When two or more ions of similar charges are present under similar conditions in a solution, for example, if we have sodium and hydrogen, and sodium ions and hydrogen ions under similar conditions, one of the ions has to be discharged in preference to the other. Example number 2, at the same time, if we have sulfate ions and the hydroxyl ions, both these are anions. And at the anode, remember, we discharge only one of the ions, so one of these two has to be preferentially discharged in preference to the other. There are three factors that we consider when discharging ions at the electrodes. The factors that we consider when discharging ions at the electrodes include: number 1, position of the metal or group in the electrochemical or reactivity series; number 2, the nature of the electrodes; and number 3, the concentration of the ions. We're going to look at each factor independently. So when we talk about factor number 1, the position of the metal or group in the electrochemical series, one thing you have to know first is that you must know the order in which ions are organized or metals are organized in the reactivity series. The ion that is lower in the electrochemical series is selected for discharge in preference to the one that is above it. For example, if we consider the anions are flowing in the order: have sulfate ions at the top, we have nitrate ions, we have chloride ions, we have bromide ions next, and we have iodide ions. Then lastly, we have hydroxyl ions. So the ease of discharge increases as we decrease down this group. We have increase in ease of discharge. The ease of discharge increases as you proceed down the group. For example, if you have a solution that has sulfate ions, and the chloride ions, of course, chloride ions will be discharged. Chloride ions will be discharged in preference to the sulfate ions. So we shall discharge chloride ions in preference to the sulfate ions. Why? Because chloride ions are below sulfate ions in the electrochemical series. When we look at the cations, cations are in the order. Have the cations are in the order. We have potassium. Number 1, we have sodium. These are ions. Have potassium, sodium, calcium, magnesium, aluminium, 3+. Then we have zinc, 2+. We have iron, 2+. We have lead, 2+ also. Then we have hydrogen, plus. Then we have copper, 2+. Manganese, 2+. Then we have silver. Silver is plus. Then you have gold. Au is also a plus. Assuming we have a solution that has two cations, for example, solution that is having calcium ions at the same time hydrogen ions. Of course, we are going to discharge hydrogen ions in preference to calcium ions. So if you're having calcium ions and hydrogen ions in the same solution, we shall discharge preferentially hydrogen ions. Why? Because hydrogen ions is below, so the ease of discharge increases as you move down the reactivity series. So here you have the increase in ease of discharge. So the ease of discharge increases as you move down those reactivity series. So therefore, we are in position to discharge hydrogen ions before we discharge calcium ions. So the same thing happens when you have hydrogen ions and then copper ions in the same solution. In this solution, it is easier to discharge copper 2 ions. Why? Because copper 2 ions is below hydrogen in the reactivity series. So we discharge copper 2 ions as we are going to look at it in the next examples. So assuming we are having a solution of copper 2 sulfate, copper 2 sulfate solution, so the ions present, so it is a solution of copper 2 sulfate. The ions present will be copper 2 sulfate aqueous ionizes to give us copper 2 ions aqueous, and the sulfate ions also aqueous. Remember, it is a dilute solution, so we have components of water that also ionize to give hydrogen ions and hydroxyl ions. So when you look at this solution, we are having two cations and two anions of different nature. We are having the cations we are having copper 2 ions and the hydrogen ions. Both these ions migrate to the cathode because they are cations. They are positively charged, so they migrate to the negative terminal, as you said before. The same thing, the sulfate ions and the hydroxyl ions are both anions. Therefore, they both migrate to the anode, where they are discharged. But not all are discharged, because we only discharge one in preference to the other. Look at the first cations. Or look at that. You look at copper. Copper in the reactivity series is right here, whereas hydrogen is right here. So hydrogen comes before copper. Therefore, we discharge at the cathode. We are in position to discharge copper before we discharge hydrogen. Why? Because copper is below hydrogen in the electrochemical series. The same thing happens when we come to the anions. The anions, we have sulfate ions and the hydroxyl ions. Look at the position of the sulfate ions. We have sulfate ions right here, then the hydroxyl ions are right here below at the end of the reactivity series. So it is simpler or easier to discharge the hydroxyl ions before we discharge the sulfate ions. So at the anode, we shall discharge the hydroxyl ions before the discharge of sulfate ions. So in our first example, we are going to look at electrolysis of dilute sulphuric acid. In some cases, it is called electrolysis of acidified water. At the end of the experiment, we are going to know why it is called electrolysis of acidified water. So we can look at the setup for the electrolysis of sulphuric acid. So the electrolysis of sulphuric acid, we are having our setup as above. We can label the diagram. We have a beaker that contains dilute sulphuric acid. We have our battery. Have the positive terminal this side and the negative terminal that side. We have our test tubes. These ones to enable us collect the gaseous products from the experiment. Then we have the anode, the positive terminal. Then we have the cathode, our negative terminal. So that is the electrolysis of dilute sulphuric acid setup. Usually it is called electrolysis of water. So can we look at the ions that are present in that solution? So ions present. So ions present. We have water that gives us hydrogen ions, aqueous, and plus the hydroxyl ions. So water ionizes in that form to give us the hydrogen ions and the hydroxyl ions. Then secondly, we have sulfuric acid also ionizing to give us the hydrogen ions, two of them, and the sulfate ions. This is also aqueous, the sulfate ions. So those are the ions present. Now when you try to look at that reaction, we are having hydrogen ions from water and sulfuric acid. Then we are having sulfate ions and hydroxyl ions from water and sulfuric acid. At the cathode, we say at the cathode. Remember, in this solution, we have hydrogen ions as the positive charged ions. Then we have the sulfate ions. Sulfate ions, of course, everywhere. Have the hydroxyl ions also everywhere. They are randomly distributed into that solution. So the reaction at the cathode will be the cathode. The hydrogen ions migrate to the cathode. So they are migrating this side. So see hydrogen ions moving this side. So wherever the hydrogen ions are, they migrate towards the cathode. What happens is that when they migrate to the cathode, of course, as we said earlier, that they get electrons from the cathode because they are electron deficient. So we're having our hydrogen ions migrating to the cathode and at the same time receiving electrons. So we put plus electrons, giving us hydrogen gas. Try to balance by putting here 2 and put here a 2, because we say 2 ions form combine to form diatomic compound or element. For example, here we have 2 hydrogen ions combining to give us hydrogen gas. That is the reaction at the cathode. At the same time, we can write reaction at the anode. So at the anode, we can say the hydroxyl ions also migrate to the anode, and even the sulfate ions will migrate to the anode. What happens? Hydroxyl ions will be discharged in preference to the sulfate ions. Why? Because we said that hydroxyl ions are below sulfate ions in the electrochemical series or the reactivity series. So the hydroxyl ions are discharged in preference to the sulfate ions. So how the hydroxyl ions are being discharged by loss. So let me first write this equation and later on I'll rectify it. So they are discharged by, because when they reach the anode, they lose the excess electrons because the anode pulls electrons from the solution. So minus electrons, giving us oxygen gas, then plus water. How do we balance this? Balance this by putting here a 4, put here a 2, then here also a 4. But it is not right to put a negative in a chemical equation. So what do we do? This one is aqueous, this is liquid. So what do? We write 4 hydroxyl ions give us oxygen gas plus 2 water molecules. Then bring this 4, negative 4 this side. When you bring this side, it becomes a positive 4 plus 4 electrons. That is our equation. So if you are asked to write the full equation from the half equations at both electrodes, so you're supposed to write the full equation. So before writing the full equation, you must first balance the number of electrons in both equations. For example, look at equation at the anode. This equation here we have 2 electrons, here we have 4 electrons. So we can easily multiply this one by 2, giving us multiply by 2, we have 4 hydrogen ions plus multiplied by 2 have 4 electrons, giving us multiplied by 2 hydrogen gas. So you can see that the number of electrons in the first equation is equal to the number of electrons in the second equation. At the end, you can easily write the full equation by adding our new equation plus the equation at the anode. Simply, we can write from the first one, we can write 4 hydrogen ions plus 4 electrons, this is aqueous, then plus 4 hydroxyl ions, 4 hydroxyl ions, aqueous, giving us the products are 2 hydrogen gas plus oxygen gas plus 2 water molecules, then plus 4 electrons. That is our equation. Then we can simply make our equation more right by cancelling out what is common both sides. Look at this side, we have 4 electrons, and this side we have 4 electrons. At the end, we can write the full equation or the final equation as 4 hydrogen ions plus aqueous, then plus 4 hydroxyl ions aqueous, giving us 2 hydrogen gas plus oxygen gas, then lastly plus 2 water molecules, that is liquid. When you look at our setup here, we are having at the anode, as we are discharging hydroxyl ions, we are having a gas here that is collected in this tube here. We are having a gas here, so this gas is oxygen gas, and around here we are having water, because in the second equation we saw that we have water. Then in the first equation at the cathode, we are having another gas that is collected around here, because hydroxyl ions, because hydrogen ions are being discharged to give us hydrogen gas. So in the second test tube here, we are having hydrogen gas. That's what we have in the second test tube. So when you try to add up these two equations, make it look more simpler, we can add these ones up, giving us 4 hydrogen ions plus 4 hydroxyl ions can have 4 water molecules aqueous, giving us 2 hydrogen gas plus oxygen gas, then lastly plus 2 water molecules. So the final equation will give us what we talked about at the beginning of the experiment. Why we call this one electrolysis of acidified water? We simply call it electrolysis of acidified water simply because the final products are all components of water. For example, look at water, hydrogen gas, oxygen gas, then lastly water molecules. So the final products are all products of water. So it is simply to, we can as well call the reaction of electrolysis of dilute sulphuric acid, you can as well call it electrolysis of acidified water. Why? Because the components or the products are all components of water. There are two important notes to note here. Number one, there are pH changes. There are pH changes at both electrodes. That is note number one. We can go through this as follows. The acidity at the cathode, around here, the acidity decreases. that is to say the pH increases. Why does the pH increase? It is because the hydrogen ions are being discharged as hydrogen gas. So you are discharging hydrogen ions as hydrogen gas, and therefore the concentration of hydrogen ions in solution decreases. Which hydrogen ions are responsible for the acidic nature or the acidity of the solution? Then at the anode, this side of the anode, what happens at the anode? The acidity increases. Why? It is because the hydroxyl ions are being discharged, and the discharge of the hydroxyl ions, look at this second equation at the anode. The discharge of the hydroxyl ions disturbs the ionic equilibrium of water, because we are discharging from this equation here. Look at this equation, look at this. Because we are discharging the hydroxyl ions, the ionic equilibrium of water is being disturbed. So more water ionizes to restore the equilibrium. That's why so at the end we shall have water again, liquid, this ionizing to form hydrogen, using these arrows, hydrogen ions, aqueous, and then the hydroxyl ions. More water is still ionizing to restore the equilibrium. Now the excess hydrogen ions will react with the incoming sulfate ions. At the end we shall cover the sulphuric acid that was previously used in the experiment. At the end of it all, we shall discover that the acidity of the solution almost remains constant. That is note number 1. Then note number 2, hydrogen gas produced at the cathode to oxygen gas produced at the anode ratio is 2 to 1. Why? Because you have more ions of hydrogen that gives us the hydrogen gas, and we have one mole of hydroxide ions giving us the oxygen gas. So that's why you see this space is smaller than this one here. So that is the end of the experiment. Next we have an experiment to show that lead-2 bromide only conducts electricity